Okay, we're continuing our discussion of the postulates of quantum mechanics. In the last video, I talked about postulate 1, which introduced the wave function and the Schrodinger equation. What I want to talk about in this video is how we interpret wave functions. And you might be surprised to learn that the answer is not necessarily obvious. There are multiple perspectives. There's not necessarily one correct answer to this question. But the basic viewpoint that we used is called the Born interpretation. Okay? Not this Born, but this Born. This is Max Born, a German physicist. And what Max said was that the probability of finding a particle in some spatial region is proportional to the square of the wave function. So how do we interpret wave functions? Well, we square it, and that tells us something about the probability of finding a particle. Pointers. Imagine I have some wave function, which is a function of x, right? It might look like this. I can square it. And that's going to be related to the probability of finding it in some region. Okay? This curve is going to tell me something about the probability of finding the particle. Wave functions can be negative, right? And so because I'm squaring it, right, that is not problematic. When I square it, you make it something that looks like this, and it all kind of works. Right? So I square wave function, I learned something about probability. But it does turn out to be more complicated than that. And the reason is that wave functions can include imaginary terms. Remember that I is defined as the square root of -1. That is an imaginary term. And so what I need to do here is give you a brief interlude on complex analysis. If you're a math minor, perhaps you've taken a complex analysis class, but most of us haven't. And so let's consider a wave function of this form. Right? Psi equals f of x plus I times g of x. F of x here is called the real part of the function, right? Because it contains only real terms. This is called the imaginary part of the function, right? Because it has imaginary and I term into it. And so what we'll do is define a quantity called the complex conjugate. The complex conjugate is indicated by the superscript asterisk. So if you see the superscript asterisk here, right, that refers to a complex conjugate. And in order to derive the complex conjugate, what you do is any place there is an I, change it to a negative I. So if I looked at some function, psi, and then I'm going to ask what the complex of that is, psi star. If I had a function which was ix, right? In order to take the complex, I take the I and I make it a negative ix. If I had a function which was negative ix, and I take the complex conjugate of it, that becomes negative ix, which is now equal to positive ix. If I had f plus ig, right, where f is some function and g is some function, when I take the complex of that, f has no imaginary part, so it stays the same. I becomes negative I, and g is g. Right? So the complex of f plus ig is f minus ig. If I had e to the ikx, this becomes e to the negative ikx. I take I make it a negative I. One more, e to the negative ikx. Again, it's not the function which becomes negative, it is the imaginary term which becomes negative. So this becomes e to the negative I kx, which is now equal to e to the positive I kx. That's how you take a complex conjugate. Right? Relatively simple and straightforward to do. We can also define something called the square modulus. Right? So the square modulus is indicated by the absolute value signs, the straight brackets. If you see that in quantum mechanics, it refers to a square modulus, not an absolute value. And the square modulus is defined as psi star psi. Right? So you take the complex and you multiply it by the function. Let's go back to our hypothetical wave function, f plus ig. Use the FOIL method from high school algebra to evaluate both psi psi and psi star psi. What impact does taking the square modulus as opposed to the square have on the imaginary terms in the product? I'm going to work through this, but if you're watching this, I would encourage you to pause it and work this out yourself. It'll take you a couple minutes. So do that. Here I go. If I do, this should be psi star psi. Okay. If I multiply f plus ig times f plus ig, you get f squared plus 2fig plus I squared g squared. F stays the same, so this is f squared. The convention is usually to write the imaginary term first, so this would be plus 2i fg. Remember that I squared is -1. So this becomes minus g squared, -1. Conversely, if I take the square modulus psi star psi, as I just derived, the complex conjugate of f plus ig is f minus ig. When I do FOIL, I get an f squared plus ifg minus ifg minus I squared g squared. Dot cancel. This becomes -1. I squared is -1. And you're left with f squared plus g squared. Right. What impact does taking the square modulus as opposed to the square have on the imaginary terms in the product? Well, you can see that this has no imaginary terms. And so this is best summarized in a cartoon, right? Cartoons never work as well when I read them to you, but bear with me. Right? Okay, anyone who's feeling like they can't handle the physics here should probably just leave now, because I'm multiplying the wave function by its complex conjugate. That's right, shit just got real. Right? Utilizing the square modulus ensures that the probability is mathematically real. Right? That is, that it has some real meaning. If I told you the probability of finding something was 0.5i, that would mean nothing. But if I told you that it was 50%, that means something. So, putting all of this notion together, right? Postulate 1b tells us how we interpret wave functions, right? The wave function has the important property that psi star psi d tau is the probability that the particle lies in the volume element d tau located at point R. That is, P equals the integral of psi star psi d tau. So, again, just to go back to this example, if I were to look at the square modulus, psi star psi, for some function Right? The probability of finding the particle at some point in this region is related to the area under the curve. Right? That's how we interpret wave functions. All right, I'll stop here. There are some example problems and another short video after this about some consequences of this, and I will see you next time.